Okay, so for the 3-1 notes here, mostly review from this section, so I'm going to go through this fairly quickly. Feel free to pause and make any notes that you need to make, but again, I'm going to try to move through this pretty quickly, not to waste your time on it. But anyway, so just a quick recap of forces, right? Forces are either a push or a pull on an object. They act on an object that is often called the agent, is whatever's causing that force. So they're acting on an object and they're caused by an agent. It's a vector measurement, which means when we deal with forces, we need to always be breaking those up into components, right? So if I've got two forces doing whatever they may be doing here, the only way that I can add those two forces is if I break those up into horizontal and vertical components and add up the components. So that's very important for the vector measurement. It also means we need direction, right? So don't forget the direction as we go through a lot of these problems. And then finally, they can be either contact or field forces. The most common field forces that we see are gravity, and then the electromagnetic force is the electric force that we dealt with a little bit at the end of last year, and we'll see again moving forward this year. Contact forces are obviously those direct pushes or pulls through tension or direct contact on an object. So anyway, quick review. Hopefully that's all pretty basics. So a quick concept check then here for you. And I know this is a little blurry on the screen here, but it's pretty clear on your handout. So 2 of 3 forces exerted on an object are shown. The net force points to the left, which is the third missing force, right? So I'd encourage you guys to try this on your own before you watch the answer here. But if I want the net force to be to the left, then obviously the third force needs to have a component going to the left that is greater than this force here. And so that actually probably helps me rule out option D, because option D doesn't move very far to the left at all. Definitely not more than this F2 component, right? And so the only way that's possible is if that component is more than that. The other big piece is if it's moving to the left, it's got to be balancing out the vertical component, because they're not saying it's up and to the left or down and to the left, it's just purely to the left. So the vertical component of my third force needs to be equal and opposite to that, right? So just kind of looking at what this would be, again, it needs to go over to the left more than the force 2, and it needs to go down an equal and opposite amount to force 1. Well, if I look at that, the resultant there ends up looking something more or less like that. Looking at my options, the closest option that I have is F3. Option C here, I guess they're all F3. But option C would be the best answer from my choices. So anyway, hopefully that one wasn't too bad. I bet you guys probably did okay on that. So then a very quick summary of some of our forces, right? Gravitational force we know is Fg. On Earth it is just mass times gravity. You also do need to be familiar with, and we will deal with this more later, but mass 1 times mass 2 over r squared, where we also have that constant of g, right? So this is my universal gravitational force. Biggest thing to realize about gravitational force, one, it is a field force, right? It's a field force. It does not require direct contact. And then it is a mutually attractive force, right? It pulls two objects closer together. Okay, so gravity is a field force and it is mutually attractive. The spring force, one of the most common forces that we tend to forget, is just simply my spring force equals negative kx, right? That's the only equation I really have for working with my spring. The biggest thing to remember from this is the negative indicates that the spring always works the opposite of the direction that the spring has been either stretched or compressed. So if I compress the spring this way, then the spring force is pushing opposite of that, right? If I stretch the spring out to where I've pulled it this way, then again the spring force is working opposite of that. Tension, obviously, usually I'll just refer to that as T. We know that that's any force within a cable. We'll see that pop up a lot here. Normal force, again, F of N. I know that this is the normal force, not because it's the average everyday force, but it's called the normal force because it's always perpendicular to the surface, right? And so the reason they call it the normal force, is normal is a geometric term for perpendicular, right? So obviously on the ground we know the normal force pushes straight up, but on an incline it's called the normal force because it's pushing perpendicular to the surface. So anyway, that's helpful to know if you didn't remember that or didn't know that from last year. Anyway, frictional force, we have two types of friction, right? We know our frictional force, and it relates to our coefficient times the normal force. We have two types, being kinetic and static, and actually we'll see later in the year we actually have rolling friction as well. We'll see that here in the next couple sections. Kinetic friction, biggest thing you need to be comfortable with is this is the friction when the object is moving, right? So this is the friction experienced when the object is in motion. Kinetic friction is always just equal to the coefficient times the normal force. Okay, so it's always equal to my coefficient times normal force. Static friction is when an object is at rest or resisting the initial change in motion. Static friction, the big thing you have to be comfortable with there is it is either less than or equal to the static friction coefficient times the normal force, right? And the easy example of that is if I've got a box that's sitting on a surface, if I only push with 1 Newton of force, then friction isn't going to supply more than that 1 Newton of force, right? So if I'm pushing with 1 Newton of force, static friction is possibly going to resist me with that full 1 Newton of force. Then if I push with 2 Newtons of force, static friction might be able to supply 2 Newtons of force. It does that up to a certain extent, so this would be considered the maximum value for static friction. But static friction could be anything less than that maximum value. So whereas kinetic friction is always a constant, if it's moving, kinetic friction is a constant value. Static friction depends on how hard the push is and what force needs to be matched in order to keep the object from moving. And that happens up to a certain limit before the static friction is broken. So good thing to make sure you are comfortable with. I think and hope you guys probably are. But if you do have any questions on either of those types of friction, don't hesitate to let me know. And then the new one for us, this is really the only new part of the next couple sections here. We'll deal with drag. We'll deal with drag, which is air resistance. We typically will neglect it unless they tell me otherwise, but we will see some air resistance. We'll deal with some functions that involve air resistance and go from there. And then finally my electromagnetic force, which is the force we dealt with at the end of the year last year or towards the end of the year last year, which was my K, Q1, Q2 over R squared. Notice this looks very similar to my gravitational force, and obviously we'll get there in due time. So anyway, quick synopsis of our forces. All of these are forces and therefore all of them can interact with one another. It's just important to make sure you understand kind of the differences between the various types of forces and where they arise. So example 1, then a bungee jumper is left off the bridge and is nearing the bottom of her fall. What are the forces acting on the bungee jumper? Well, if she's nearing the bottom of her fall, right, so the bungee cord at that point is starting to stretch out a little bit, right, so here's the bungee jumper down here. Well, near the bottom, obviously we have the force of gravity always pulling her down, right, but if it's nearing the bottom of her fall, then we know that we have the tension, or actually in this case I would probably refer to that as a spring force, because the bungee cord is elastic, right? So I have the spring force that's pulling her back up. And if she's nearing the bottom of her fall, so for part A I've got those two forces. For part B, if she's nearing the bottom, which of these forces, if any, has a larger magnitude? Well, hopefully as she's nearing the bottom, she's starting to slow down, right? So if she's falling downward, if her velocity is going downward, and she's starting to slow down, that tells me the acceleration, and therefore the net force, would be going upward. So if the only two forces acting on her are the spring force of the bungee cord and the force of gravity of her weight, right, if the net force and the acceleration are going upward, then that tells me the spring force, the elastic force in that cable, has to be greater than her force due to gravity. In order for her to slow down before she springs back up the other direction, the spring force again has to be greater than the force due to gravity. So question 2 here is just a good example of a free body diagram, and there are some specifics that I want to make sure we're all comfortable with here, because particularly looking at the key from last year's test, I noticed that they did have a few specific points that they either awarded or deducted based on these free body diagrams. So anyway, let's think about all of the forces that would act on this skier as they're being dragged up the incline. Okay, so first and foremost, I know it's a constant speed, right? So it's a constant speed, which tells me that the net force is 0. Okay, so as I look at this problem, again, free body diagram should show only the forces that act on it. I don't want any components, I don't want any velocities, I don't want any distances, right? Just any forces acting. So the first force probably most of us would be comfortable with is our force of gravity, which pulls straight down. We also then have the normal force, which pushes perpendicular to the surface. And honestly, as I'm doing this free body diagram, I would probably indicate that's perpendicular by making myself that right angle, just so I do show my understanding that it's perpendicular to that surface. The other thing that I would try to do, and it doesn't have to be perfect, but it should be close, that normal force should be pretty close to the vertical component here of my force due to gravity. So again, I've got my force due to gravity. I'm not actually going to draw this leg of that gravity in because that's not actually its own force, but the normal force here should be pretty close to equal to that magnitude of this vertical component. Okay, so again, I don't draw in those components, but it is good to be thinking about those components. So then the only other forces we have obviously are working either up or down the inclined plane here. So yes, again, I do have a component of gravity pulling down the inclined plane, but that does not belong on my free body diagram because that is only part of the gravitational force, and therefore it is not its own force, so I don't put it on here. Okay, so instead, I know that they're being dragged up by a friction, or excuse me, by a tension, since I have a tow rope. So I've got a tension then pulling up the ramp, right? So I have whatever that tension may be going up the ramp. And then the forces that I have pulling down, well again, I have that component of gravity, which I'm not going to draw on here, but I do need to think about. And then I have two other forces that would be working against her. I've got the friction between the surface and the ground, and then I have the air resistance between her and obviously the air, right? So I do have both of those forces working against her. So friction, and then I'll call this D for drag. So I've got all of those forces then that I've labeled. The one thing that I would be very careful with is tension should definitely be bigger than both the drag and the frictional force because I also have this component of gravity pulling down the ramp. So just like I said, the normal force should be pretty much equal and opposite to this. The tension force pulling up the ramp should be equal and opposite to D, friction, and this component of gravity, which I'm not showing. So really tension should be more than both the drag and the frictional force going down the ramp. So rolling right along here, quick check number 2, you've just kicked a rock. It's now sliding across the ground about 2 meters in front of you. Which of these forces act on the rock? List all that apply. Well, if we've kicked it and it's now 2 meters in front of me, the force of the kick no longer acts, right? So option C is a little bit of a distractor there because it's no longer in contact with the force. Okay, so obviously I do have gravity. So list all that apply. I do still have gravity, which is pulling down. I do still have a normal force, which is acting upward. And then I do have frictional force, which is causing it to slide and then slow down, right? Okay, so all three of those forces I have, but I no longer have a force from the kick because it is no longer in contact with my foot. So then another review on this page between mass and inertia, and then we throw in inertial mass as well, which actually is a term worth noting. It is a term worth kind of understanding as I go through that here in a minute. Right. Mass is simply the amount of matter making up an object. So we measure mass in kilograms, but always think of that as just the amount of matter that something has, right? We know that mass is a universal measurement. It doesn't change depending on where we are, right? Weight is a relative term. Mass is constant everywhere as long as that object has not changed in structure. Inertia is the tendency of an object to resist a change in motion. Okay, so typically the inertia is measured through mass, but really inertia in its simplest form is just the tendency to resist a change in motion. Inertial mass then is the measure of an object's resistance to changing motion. Okay, so when we talk about an inertial mass, what we're really looking at there is what is the resistance to change. So there's two types of masses that we'll deal with in this course. There's inertial mass and there's gravitational mass. Gravitational mass obviously comes from basically just working with the force due to gravity and the weight. Inertial mass, on the other hand, would come from if we were doing an experiment to find out the acceleration of an object, right? So if I was doing an experiment kind of like we did last year where we had the cart set up and the blocks hanging over the table, right? That was really testing the inertial mass and the tendency to resist a change in motion, right? As I add more weight to this, or as I add more weight to this, right, particularly if I add more weight to this mass here, this object resists change more and more and more. So the inertial mass is really just force equals mass times acceleration, where I'm studying what's the acceleration as a result of the force. Because if the inertial mass is higher, obviously that acceleration under the same force would end up being lower. So it is no different than just mass, it's just a specific way of thinking about mass as we go through.